Good listening. I'm Jane Zhao from Shenzhen Technology University. I will present our paper, blockchain-based decentralized gradient aggregation design for federated learning. This is a cooperation work with colleagues from Tsinghua University and Dongguan University of Technology. The content of my talk include 5 parts. The first one is our research motivation. The second one is our contributions. The third one is our proposed decentralized system design. The fourth one is decentralized leader selection algorithm. The last one is the evaluation and results. Nowadays, we are concerned about our data privacy on the internet. Many personal data disclosure accidents happened. The artificial intelligence technology usually requires large amount of data for learning. This results great data security problem. Researchers proposed federated learning to alleviate this impact. In federated learning, users do not need to upload their local data to central servers for training. They just exchange partial gradients. There are usually 2 architectures for gradient aggregation. There are centralized ones and decentralized ones. Most existing federated learning systems are mainly based on a centralized architecture, just like Figure A. It uses third-party collaborators to enable each worker node to perform training. The collaborators aggregate workers' gradients and then pass the updated parameters back to worker nodes. This centralized architecture is vulnerable to recovery attacks. Some researchers have reported that the original data can be recovered if the attacker can collect enough gradients from the workers. Therefore, centralized gradient aggregation is not secure in protecting users' data privacy. We study how to achieve decentralized gradient aggregation based on blockchain technology. Our contributions are in 3 folds. First, we build a federated learning system with both control layer and data layer. The coordination is fulfilled by control layer, which is not in a centralized form. The large data transmission is fulfilled by data layer. Second, we design a decentralized algorithm for gradient aggregation to reduce the risk of data privacy disclosure. Lastly, we validate our design and algorithm through real-world experiments, which shows the effectiveness of our system. Our system design applies blockchain technology to aggregate gradients instead of central servers. The design principles include 3 points. First, as of no central servers, we use smart contracts to serve as an entity for coordination. Second, the system includes control layer and data layer. This is because blockchain technology is not suitable for large data transmission. Third, the system should be effective in model accuracy, training time, and data privacy protection. This figure shows our system architecture. The blue part shows the control layer, which is implemented using smart contracts. Smart contracts are programming codes running in blockchain platforms. They run in every node in the blockchain platform, but act as an entity providing some service. The white part shows the data layer. In this layer, nodes perform the local training process and upload gradients. In data layer, the workflow of nodes is as follows. Every node performs local training. Then every node acts differently according to its role. For worker nodes, they upload gradients to storage and register the gradient path in smart contract. For the leader node, it collects gradients in one round and performs aggregation. The leader node uploads aggregation resulted parameters and registers the parameter path in smart contracts. The worker nodes then fetch the aggregation results to update local model. The control layer is implemented using smart contracts. It needs to perform the leader selection, and it needs to record the aggregation time of leaders, the shared gradient path from workers, the aggregated parameter path from leaders. We will describe the leader selection algorithm in the coming slides. Blockchain technology is very suitable for deploying decentralized applications. Every node is able to get the service provided by smart contracts. How will the smart contract select the leader? There exists a trade-off between randomness and performance. On one hand, data privacy protection requires leader selection to be random. On the other hand, good performance requires nodes with better resources to act as leaders. To achieve a good trade-off among them, we design a leader selection probability distribution. Let T be the time of one node completing the gradient aggregation. The weight of one node L being selected as the leader is WL, which is a logarithm function relevant to time t and the balance factor lambda. The balance factor lambda is used to adjust the trade-off. We evaluate our decentralized system design for federated learning to show its effectiveness in model accuracy, training time, and leader randomness. We deploy the smart contract on Hyperledger Fabric. We use the MINIST dataset for training a CNN model. The model contains two convolutional layers, two fully connected layers, and one output layer. Each node has 5,500 training samples. Let's first see the training accuracy of our system. We simulate 10 nodes for two cases. The left figure shows the case of nodes having real local samples, only 50 data samples for each node. The right figure shows the case of nodes having sufficient local samples, that's 5,000 data samples for each node. The horizontal axis represents each node. The vertical axis represents the accuracy. For real local sample case, each node achieves 8.4% accuracy improvement compared with training alone. For sufficient local sample case, each node achieves 1.2% accuracy improvement. We evaluate how the model accuracy will change with the number of participating nodes. Here we see the model accuracy of a single node improves as the number of participating nodes increases. This result shows how a system achieves the effectiveness of federated learning in improving model accuracy. Second, we evaluate the time performance of our system. We check how the time for gradient aggregation changes with the balance factor. For the completely random leader selection, the average time for gradient aggregation is about 10.5 seconds. Our leader selection mechanism will save up to 35% of the time when balance factor is 100. And this saving can be adjusted through the balance factor change. Lastly, let's see the randomness of leader selection. We statistic the number of one node being the leader during 500 training rounds. In the left figure, the number of one node being the leader is between the blue line and the yellow line. We can see it can be adjusted by the balance factor. In the right figure, we compare our approach with completely random one and performance priority one. Our approach achieves an adjustable trade-off among randomness and performance. That's my talk. Thank you for your listening. Any questions?